Okay, so I think that the question is about this displacement problem, which is really an expression or an application of what's called the net change theorem. And it sounds kind of cool, but it's actually a theorem that doesn't say all that much that we didn't already know. The net change theorem says if f prime of x, well, this is pretty obvious, is a derivative of f of x. I mean, I wouldn't really have to say that because when we write f prime of x, we assume that's a derivative of f of x. Then the definite integral from a to b of f prime of x dx is equal to the net change in f of x from a to b. This function f of x and f prime of x can be any function, so they could represent distance is very common for f, but it could be quantity of water, it could be profits. There's lots of different possibilities there in terms of what we could be representing with that function. So this is like an application, but this statement here is not surprising at all from our understanding of the fundamental theorem of calculus, right? Because the fundamental theorem of calculus says that when I take the antiderivative, the fundamental theorem is really saying that this definite integral is really like an antiderivative. And so when we evaluate this, we get the antiderivative of f prime. The antiderivative of f prime is f. Now, we have to be a little careful here because, you know, f is a specific function. And so when we take the indefinite or definite integral, we may not get back exactly the specific function f, right? The constant is an issue there. But when you're working with this definite integral symbol, it's not going to matter because whatever constant you have, you know, if it was f of x plus c or something like that, you would just add the c and then subtract the c here and it would drop off in the end. So this isn't telling us exactly what f is, it's telling us the net change in the function f. Okay, so there is a little bit of, I guess you could say, subtlety there, but it's not anything that we have to really concern ourselves with. And when we think of it this way, this is a very, it's accurate enough to think of it this way, right? And this is what the fundamental theorem of calculus says. And this is exactly right here. This is what we call the net change in f. That's what it is it's where you end up minus where you started. F of b minus f of a. That's the net change, and that is what this expression is giving us. So what we want to distinguish there is that the net change is not the same as the total change in the function f. And what we mean by that, or a good example of that, is that if you imagine a particle that's sort of moving, and we're interested in sort of how far it moves, that might be a position function. You know, the particle might move like this. Okay. And so the net change would just be where I ended up minus where I started, which would be exactly this distance here. But the actual distance traveled is quite a bit more, right? Because it went forward for a while, then it went backwards, then it went forward for a while. So the net change is not describing everything that's going on. It's just a difference between where you started and where you finished up. That's what the net change is giving us. And so the classic example for that is if I give you an actual position function, say, well, I give you a velocity function. Say this is 2t plus 5. Make that more interesting. 2t minus 6 on the interval from 1 to 5. So we have here a velocity function. So you know the velocity of this particle. And the question is, there's two possible questions here. Well, I suppose there's lots of other questions here, but the two questions that we're interested in are A, what is the net change in position? And B, what is the total distance traveled? And these are potentially different things, as we can see by this example, right? The distance traveled here is more than the net change. And so the way to figure this out is when it's asking for net change, well, that's just a straight integral. I don't have to overthink this. Velocity is the derivative of position. So I'm just going to integrate this velocity function from 1 to 5. Using my rules of antiderivatives, this is going to be t squared minus 6t from 1 to 5, right? Antiderivative, antiderivative. It's going to be 25 minus 30 minus 1 minus 6, right? So notice how I do that. I put in 5 for both of these, and then you don't need those parentheses, but it's nice to sort of keep track that this is my 5, and that's what happens when I put in 1. 25 minus 30, I get minus 5, and that's what, plus 5? Well, that equals 0 in this case. A little bit of a coincidence there, but that's what it is. Does that make sense? Is that possible? Could the velocity certainly is present here. How could I have a net change in position that's 0? Well, let's take a look at it visually from 1 to 5. This is 2t minus 6. And so up 2 over 1. And so that's my velocity function. So when I integrate from 1 to 5, what I'm getting is exactly, I kind of messed that up because it actually crosses in the middle there, right? 1, or sorry, in the middle there. 1, 2, 3, 4, 5. I kind of mangled that, but the axes there. But can you see then, of course, that this is going to be 0 because this portion and that portion are exactly equal, but they're going to be opposite signs for the integral. So that's going to be 0. The total distance traveled, though, is something. What happens is at 1, the velocity is negative, so this particle or person or whatever is moving backwards. And then at some point, right here, the velocity is 0, so it moves backwards, then it stops, and then it moves forwards, and what we're claiming is that it ends up at 0, but it did travel some distance. So in order to figure out that distance, I need to figure out right where this, oh, I see the problem, 1, 2, 3. I Actually, my graph wasn't too bad. I was just counting wrong, right? I was counting this at 0, but it's really 1. So 1, 2, 3, 4, 5. There we go. So in order to break this up, what I need to do is figure out where the velocity is 0 and then split those into individual integrals. So in this case, I know what that's going to be. It's at t equals 3. In some other problems, you'll have to solve for that. And then I can integrate here from 1 to 3, 2t minus 6. And I want to make sure that that's a positive because I'm looking for distance. Right? Distance traveled is a positive value, like an absolute value. I would also have to do the second part as well. However, in this case, I know those are both the same. So in this case, I can just double whatever I get. But so that's the same antiderivative, but now from 1 to 3. So what do I get? 9 minus 18. So this negative here, I'm like going to be really careful of because that's got a whole bunch of negatives in this problem. That's an easy way to make a small and unfortunate error. Right, so that's putting in 3 and then minus the negative, putting in 1. And what do I end up with here? This is minus 9, so that becomes 9 minus 5 equals 4. As I said, I had another 4 there, so this should be 8. And of course, we could have, in this case, we could have figured that one out this one out by geometry as well, right? That's a 4 by 2, so that does have area 4. Does that answer the question? Okay,
yeah.
Okay. All right. Good. So yeah, again, as I say every day, right, there's 2 parts here. There's the understanding what we're trying to do and what you're being asked to do. But then there's the second part, which is actually doing it, right? Calculating the values properly, finding where it's 0, finding those antiderivatives, kind of breaking through the problem that way. But you can't do that work until you understand kind of visually what this is kind of asking. So net change, total distance traveled. Net change is certainly easier because you just integrate it. That's exactly what the definition says. The distance traveled is a little trickier because you've got to kind of break it up and think about what the problem is doing. And the biggest issue there is just positive and negative. If the function is always positive or always negative, then the net change and the distance traveled are going to be the same, right? If I'm always moving forward, then no matter what, the distance I travel is equal to where I end minus where I started. We only run into some differences when we have a positive and negative velocities. And again, velocity and position are the kind of the easiest for us to grasp and work with, but this applies to any function and its derivative. So it's kind of a start of seeing the kind of power of this. And it's really answering some questions that you might have about a function. It tells us what a function is doing. Other questions? Anything else? Okay. Well, let me introduce 5.5 here for us then, since there weren't any other questions from 5.4, which I think is reasonable. A lot of remember 5.4 was working with the indefinite integral, which is really just the antiderivative. In 5.5, we're going to look at a strategy called substitution. So substitution is a method for finding antiderivatives. And we, of course, need antiderivatives because of the fundamental theorem of calculus, right? That we want to be able to evaluate the definite integrals. Antiderivatives have other uses too, but for us right now, we're really interested in trying to figure out how to find these definite integrals, right? From A to B, we'd like to find the antiderivative. To do that, if you've done your work from 5.4, you've seen, well, it's not always so straightforward, but you can usually figure out what those indefinite integrals are. In 5.5, we're using substitution, which is a method for reversing the chain rule. Okay, so the idea is if I have, say, a function the sine of x to the fifth, let that be my function, then the derivative f prime of x, if we're going to find the derivative of this, we're going to take the derivative of the outside evaluated at x to the fifth times the derivative of the inside 5x to the fourth. Our goal, right, this is like this direction is the derivative. So this direction is the antiderivative. And of course, you know, you can have a constant in there in different places, right? Whatever the constant is that's in there, you're still going to get the same derivative. And that would then be our antiderivative. So we want to recognize that and look for that. And sometimes you might be able to just see it, right? Like maybe this one, when you look at it, you're actually able to see, that is the chain rule. But there's a lot of other problems that you are not going to be able to see directly that pattern. And we need a sort of strategy or a formalized strategy to make that work for us. The other thing you should notice is this is a little bit of an exception to the rule of not being able to deal with products, right? When we look at this, this is a product, but it's a very special kind of product because of the relationship between these pieces. This is actually the derivative of that, right? And that's this critical relationship that comes from the chain rule. So again, just to remind you, the derivative of f of g of x is f prime of g of x times g prime of x. And again, same rule. This is the derivative going left to right, the antiderivative going right to left. And just as before, this piece here is kind of the crucial pairing that's allowing us to rewrite this or evaluate this indefinite integral. Okay. And so finally, our rule here, stated as an antiderivative, is that the antiderivative of, I'm going to write it like this, f of u du is equal to capital F of u plus c. And the u here is some or any function of x. and du is the derivative of that function, g. Okay. So that's the kind of theory behind this, is that these are all really like kind of saying the same thing, just in slightly different forms. But the theory is this, right? That this special relationship can be unraveled to find the original function. But then we need to learn how to apply that theory, the sort of structure of applying that theory. And so let's try an example and see how we can set this up. Let's try and find the antiderivative of x squared minus 2x to the fifth Okay, so our perspective here, how I'd like you to see or think about this problem, is to say, first of all, okay, this is an antiderivative, right? When I look at this, I see a product of two functions, and that I don't know how to solve directly. And if you remember our strategies from Tuesday, one option is to say, is this, maybe I should write that over here. Number one, is it a direct derivative? Right? And there's no function whose derivative, none of our like standard functions whose derivative is this, right? That's not it. Number two, if it's not a direct derivative, can I simplify it so that it is a direct derivative? And now here, you actually could simplify this, but you would have to raise x squared minus 2x to the fifth. It's theoretically, I mean, it's more than just theoretically, it's definitely possible, but it's not particularly fun, right? To do a binomial to the fifth. There are some shortcuts and things, but it'd be a mess. So we don't really want to do that. Our only other option is substitution. It's one nice thing actually about Calc 1 is that you don't actually have very many tools. When you get to Calc 2, all of a sudden you'll realize or see a whole bunch of different things, and it will be hard to choose what to do. But for us, it's really one of these two. Either we can simplify it into something that works, or we need to use substitution. What I'm looking for to apply substitution is I'm looking for this relationship, a g and a g prime within the function. If I can make that sort of substitution, I'm going to be able, hopefully, to find the antiderivative. Again, this is not a guarantee. This is not going to work in all cases, but it is a strategy that is useful and will work in these cases, chapter 5.5 type cases. So what I notice here is that there's that relationship between these two parts, right? This is the derivative of this. So that tells me that I would like to make a substitution. I'm going to replace x squared minus 2x with u. Okay. The derivative of this g is 2x minus 2. And this kind of second part of the rule says that I can replace 2x minus 2 dx with du. So this dx and du actually come from differentials. This little formula on here is really from differentials. it's not something I expect you to remember offhand or to see how it applies here. It's really fine to just keep it as kind of a placeholder. Like this is just how I work with the substitution rule. Okay. If you want to get more into it, we can certainly talk about it a little bit more, but it's not so important. It's not really a sort of conceptual thing going on here. This is just a strategy to help us find the antiderivative. It's a lot like factoring in that there's lots of different strategies and tools, but in the end, all we care about is that we can take this polynomial and turn it into this product, this factored form. And if you get the right factored form, then you're set. Same thing with antiderivatives. So this process can help us and does help us, but it's not indispensable, right? It's just a tool. Okay, so let's see what we have here. This then becomes, using these substitutions, I can rewrite the expression as u to the fifth and the 2x minus 2 dx, that whole thing gets replaced by du. And that's what the substitution rule actually tells us, is that I can do this integral or this integral, that they're actually going to be the same. And this integral is one I know directly. This is just a power rule. U to the fifth du is going to be u to the 6 over 6 plus c. And my last step is just to go ahead and replace the u with the x. The u was my own invention. Right? I don't want the u in my answer. Nobody asked me for what it was in terms of u. They wanted it in terms of x. Right? They wanted this expression. And I think you can hopefully see what happens when I take the derivative of this, right? The 6 cancels with the 6 on the bottom. And I get this to the fifth times the derivative of the inside, which is exactly that, right? So this is the antiderivative of that expression. Okay. Questions about that example? Feel like we should see another, right? That was a process there. Let's see if we can make it more clear. Let's try. Let's try the antiderivative of e to the tangent x times secant squared x dx. And both of these this one and the previous one are considered very straightforward examples, because the du, which is like the derivative of the inside part, is just sitting there for you in the problem. You just have to see it. You don't have to do anything to make it happen, right? Some of the later problems that we'll see in this section, you have to do a little finessing to get everything to fit together. But this one, we're hoping you can see like the last one. So why don't you just take a minute and see if you can figure out what this antiderivative is. And, you know, I think I'm sure that some of you can see it, and that's great. If you can see what it is, you should totally just write it down and check your work, and you'll know if you have it or not. But we also do want to make sure that we're able to practice our strategy here, because we're going to need that when we see some harder types of problems, right? So we're sort of trying to figure them out, but we're also trying to build this strategy. So the U that we use is always like the inside piece, which here is tangent. And the du, then the derivative of tangent is secant squared. So once I pick u, du is determined entirely from this substitution. I don't look at what's up here anymore. Once u is chosen as tangent, du has to be the derivative of tangent, which is secant squared, times dx. Now it just so happens that is exactly what is here, and like I was saying, that is fortunate. So that's e to the u du, so I can treat that just as the antiderivative of e to the u, which is e to the u plus c. And then I make my substitution there, e to the tangent plus c. This is one I can certainly check my work and see it. But some of them will give you derivatives that are actually fairly challenging to check. I mean, you can always do it because we can take the derivatives of lots of things, but if it's a big messy one, sometimes the checking may or may not always work. Right? But one like this, I would take a second just to make sure this is, the derivative of this does give me exactly that. All right, let's try. Let's try that one. Now, this one is more subtle. It's not nearly as clear what the right strategy is. It looks a little bit like arctangent, but it's not quite. That x on top changes it. So it is not arctangent of x. When you have a variable like that, you can't just, it changes it in a substantial way. So it's not just a version of arctangent. So it turns out it is not a direct derivative, not a direct formula, we know. So our only other option then is to simplify it, but this doesn't simplify very easily because we have 1 plus x squared on the bottom, right? If I had 1, if it was flipped, that'd be different, right? I could simplify using the x, but it's not. It's x over 1 plus x squared. So because I can't simplify it and it's not a direct formula, my only other option is substitution. So I need to pick a u and pick a du. And this is where there is a little bit of a, should we say, art form in picking the u and the du. It is something you will learn as you do more of them. You'll get better at making the right guess, but it's often still a little bit of a guess. It's hard to know always what's the right strategy here. A general rule is that I don't want to pick, or the way I like to think about it is I don't want to pick u to be too big or too small. I want like the Goldilocks u. I want it to be just in the middle, okay? So an example of that is like, I don't want to pick u to be like this whole thing. because then the derivative of that is going to be a kind of a mess, right? It's going to be like a quotient rule. And I've kind of used up everything with u. There'd be no, I wouldn't have any extra parts to be substituted in for du. So that would be an example of like too big. Okay. It's not crazy to think of u as being just x squared, but it turns out that's actually a little bit too small. I want to kind of fundamentally change the problem here. So it turns out that that is a good u. And it is not uncommon to let the denominator, when you have a fraction, it's not uncommon to let the denominator be u. So in the things that there are to try, that's usually a pretty good try. Again, there's no guarantees here. This is not a formula where you always do step A, B, and then C and get the answer. This is a experimental thing where we try and fit the pieces together. Okay, so if this is my u, then my du is 2x dx. Again, that comes entirely, I blocked off everything there, right? That comes entirely from the u. Once I've chosen u, du is determined from that. And so when I look at this, this is fine, right? 1 plus x squared is going to be u. But I have a little bit of a problem here, right? This is supposed to be, to get du, I'm supposed to have 2x dx. But I only have an x dx on the top. Turns out that's fine. A constant can be adjusted because a constant multiple can actually kind of move in and out of the antiderivative. It's not going to affect the derivative, so it's not going to affect the antiderivative either. So what I like to do in this situation is to say, okay, well, I'd like to have a 2x dx. So let's multiply on the inside by 2 and compensate on the outside with a 1/2. Right? That's really like doing nothing. Multiplying by 2 and then multiplying by 1/2. But it allows me then to have the right substitution there. The book and other people do something very similar, but what they might do is divide this by 2. And then they could replace x dx here with du over 2, which is going to be exactly the same spot in the end. So that's purely just a matter of preference. There's not really any substantial difference there. You can either kind of add in what you need to get the right du, or you can divide so that you get the right du. So the 2x dx on the top is du, and the 1 plus x squared on the bottom is x, sorry, u. Keep your variables straight here. 1 plus x squared is u. So this is du over u, and that's a very common antiderivative. Du over u is the natural log of u plus c. Do not forget to put back in what u is. I often will get questions on WebAssign saying, I'm sure this is the right antiderivative, and people will have written 1/2 natural log of u plus c, which of course is not quite right, just because they forgot to substitute that in at the end. Any questions about that?
Yeah, so you're saying once you find your u by kind of guessing and then find the derivative of like du, you have to go back and adjust the problem, correct?
Yeah, the goal, is to turn this antiderivative, which we don't really know how to deal with, into this antiderivative, which we do know how to deal with. And substitution right here, I feel like I'm a little laggy, but substitution right here is the tool that we use to change this one into this one.
Right, got it.
And it's really, I'm not actually changing it in that it's not really any different. It just looks different. It looks different in a way that I'm able to find its antiderivative. Perhaps if we had a different way of thinking or looking at the world, we could do it directly from this, but we don't, or I don't. And so we need to kind of change it into this to help us find the antiderivative, and then we change it back afterwards to get our final answer. So it's like an intermediate step to help us, and then we want to revert back to the original once we've gotten there. And you're right in that we kind of guess the U, right? It's like, especially in the beginning, you won't always know what this U should be. You got to try something. And if it doesn't work, that's fine. Go back and try a slightly larger piece or a slightly smaller piece to be your U. And there are some integrals that I will see and I'll look at and I'll say, ooh, I don't quite know what I should do here. But I try some things, and usually I can figure out what it might be. So don't think that there's some sort of magical step that you're missing. It's just some experience and kind of imagining what would happen. I find the analogy is really similar to, like, if I give you x squared minus, I have a good example here. Minus 3x minus 56. And I say factor. So, like, you know, everybody has kind of different strategies for how they are going to figure that out, but a common one is sort of some trial and error, right? And I think, like, okay, well, what might work here for 56? What are the factors of 56? You know, this is kind of like the substitution phase. Like, how can I kind of break this down or make it look a little differently? And then, you know, eventually, hopefully get to what, maybe this doesn't even, maybe it's a terrible example, right? Because it doesn't even factor. Change that, right? Instead of 56, I'll just go with like 24 or something, but it's better too. My factoring is all messed up here. It's trying to make something more interesting than it should be. There we go, 36. So, like, factoring for us is a kind of trial and error process, and we kind of experiment until the pieces kind of lock together and fit together. And once they do, minus 9 and, oh man, what is wrong? I'm so distracted by, does this factor? I don't know. 1 and 36, 2 and 18, 3 and 12, 4 and 9, 6 and 6, but none of those differ by 3. I picked another terrible. I guess I have a hard time shifting gears, right, from calculus to not calculus. So maybe that's a bad example because I'm not supposed to make it look hard, right? It's supposed to be something similar for us. But the idea here is that I'm taking a problem and and trying to turn it into something else. And I can kind of check that problem by reversing the process, right? Multiplying it back to see that it works. And so we have this kind of feedback loop between the two. We don't care so much what the process is that gets us from here to here, right? Different people are going to think and look at that in different ways. And we don't care. Sometimes you'll just see it. Sometimes, like me, you'll flail through it, but eventually you'll get there. And that's the same idea with these antiderivatives, right? So try some things. If it doesn't work, go back and try some other things to make it work. Right? And that sometimes is hard for students because it's not how we deal with a lot of math, right? A lot of math is every step is moving us closer to the answer. This is a little more like step, it doesn't work, step, doesn't work. So you got to adjust your process a little bit. Okay. Be a little careful with substitution. I had some, if you guys had more questions, I would have maybe just saved substitution, but I think it's good that you saw it. It'll certainly important as we get through into 5.5, right? Because that's where the substitution is.